Hi, thanks for attending the CVPR 2020 virtual tutorial on visual recognition for image, video, and 3D. I'm Haoqi Fan, a research engineer from Facebook AI Research Computer Vision team. Today, I will talk about one of our major video efforts on facilitating video understanding research for the community, where I want to introduce you to PySlowFast, the video understanding codebase in PyTorch. The target of having PySlowFast is to provide a high performance, lightweight, and very efficient codebase which support state-of-the-art video backbones for video understanding research on many different tasks. Tasks like video classification, action detection, multimodality understanding, self-supervised learning, and etc. PySlowFast is designed to support the rapid implementation and evaluating your new brave ideas for video research. Before we dive into the detail about PySlowFast, I'd like to quickly share you some high-level view of the relation between image and video, especially to the people who are familiar more about the image counterpart. We can start with a two-dimensional space with axis of h by w, where we can see there's a square and the color of blue in the middle of the screen, which can represent an image. In order to have the video counterpart, we need a third dimension of t. The next thing we need to do in order to get the video is to grow more information along with the dimension of t. Then, by densely fit more continued information along with the dimension of t in a differential manner, we could have a cube here to represent the spatial temporal information from the real world. However, because of the design of the camera and because of the limitation of the computing, we could only able to process non-differentiable, non-continued spatial temporal snapshots sampled from the original spatial temporal space. After sampling from the original spatial temporal space, we will have a sequence of frames to represent the so-called video, which is the main thing we play with. So, by showing us how to bridge from image to the video counterpart, one of the major property we can learn is because of the introducing of the new dimension of t, processing video will be much more computational heavier than its image counterpart, which suggesting that a code base with efficient training will be highly valuable. Secondly, a unique property of video compared to its image counterpart is video would able to carry more modalities. For example, video could carry modalities like RGB, optical flow, or audio information, which suggesting that a code base with the ability of processing multimodality information will be highly valuable. Last but not the least, video is an old and young field. The history of video could be backtracked to dozens of years ago, which makes it a field with one of the longest history in the computer vision. But in the meanwhile, because of the recent effort on large-scale visual understanding, people started to have more breakthroughs on this field, which also make it a young field, which is suggesting a code base with comprehensive state-of-the-art benchmarks will be highly valuable. Because of the motivation discussed here, we want to introduce our video understanding codebase, PySlowFast. PySlowFast is an easy-to-use video understanding codebase in PyTorch for advanced modeling and state-of-art research tasks. Before we get into detail of PySlowFast, I'd like to share the timeline or the history of the codebase along with some of the important past video research works from our team. It all starts from 2018, where the team had a paper called Non-Local Neural Networks, which the paper introduced the non-local operations as a generic family of building blocks for capturing long-range dependencies. After that, moved to 2019 October, we introduced PySlowFast network, a two-pathway network with a slow pathway to capture spatial semantics and a fast pathway to capture the motions at a fine temporal resolution. And the work won the AVA challenge on the track of spatial temporal action localization at the same year in CVPR 2019. Move to November, we have the PySlowFast codebase firstly released. It's the ICCV 2019 tutorial on visual recognition for image, video, and 3D, with a version number of 0.9. Then, the same year, on December, we have released the version 1.0, with the video detection part implemented. And in the meanwhile, we also released the AVA challenge winning model zoo to share it to the community to reproduce our results. Then next year, there are two papers from the team got accepted by CVPR 2020 as an oral paper. The first one is the X3D network, expanding architecture for efficient video recognition, a family of efficient video networks that progressively expand a tiny 2D image classification architecture along multiple networks axes in space, time, width, and depth. And we also have the paper multi-grid, a multi-grid method for efficiently training video models, a simple effective method that significantly speed up the training speed. And this month, 2020, June, we are open sourcing the two papers, X3D and multi-grid, along with more support on different datasets in PySlowFast. Many people are also interested in our work on audio-visual SlowFast, which is an architecture for integrate audio-visual perceptions. We are working on open sourcing it, along with more components on the video self-supervised learning. Since the release of PySlowFast during the last ICCV, we have collected more than 2.5 thousand stars with more than 600 clones and 17,000 of views from the internet. Now, we're getting back to discuss on more details about PySlowFast codebase, which, as I said, it is an easy-to-use video understanding codebase in PyTorch for advanced modeling and state-of-art research tasks. We could break this long sentence into three keywords: easy to use, modeling, tasks. So in the following presentation, I will visit these three keywords in order. First, we want to discuss the keyword of easy to use. PySlowFast is designed to be very easy to hack, which suggests that you're able to encourage to directly modify the code on top of it, and the code base is designed to support rapid implementation and evaluate your new, novel, brave ideas very quickly. In order to facilitate your research and speed up the research cycle, In PySlowFast, we provide a comprehensive list of training recipes on different datasets with different type of methods. For example, if you clone the codebase and simply list the YAML config files under the config folder, you will see a lot of different YAML files sit there with different dataset folder like Ava, charade, kinetics, something, and others. And each of them will support different type of models, from some standard C2D, convolutional 2D models, to some high capacity SlowFast models. We are still trying to grow the size of the model zoo and to make it support even broader range of the models. If you check any of the config file, you will find some YAML config look like what we have on the right side. And more importantly, the recipe is reproducible, which means when you get your environment correct and get your data properly downloaded and preprocessed, then by simply running the training code with the same YAML we provided, you will have the same curve and the same performance as released in the paper. By playing with the config, you could decide what dataset you could want to train on. For example, here we are having a kinetics dataset as a training set. And you could also decide what kind of model you want to play with, and what is the training recipe, and of course, how many machines you want to use. By simply changing the dataset from kinetics to Ava, you are able to train your network on Ava dataset. And if you want to play with some backbone with higher capacity, then you can simply replace the architecture from i3D to SlowFast. Then the model builder will help you to build a SlowFast model. You could also change the learning rate schedule with some cosine learning rate. Train your network with 8 machines by simply replace the 1 to 8. Beside the YAML, we also provide the corresponding pre-trained models, which means you can directly take the model off the shelf and test it or fine-tune it on many different datasets or many different tasks you're playing with. So here is an example snapshot of the pre-trained models we provided, from the simplest 2D convolution to some higher capacity networks like SlowFast. Note that these networks are trained and tested on the Kinetics 400 dataset. Besides of releasing the pre-trained model on Kinetics dataset, which is one of the most standard tasks for video representation learning, we're also releasing a large model too on many other different datasets. For example, here, this is another snapshot of the model we provided to the users, which is the pre-trained model for AVA dataset. We're also releasing pre-trained models for many other datasets like something, and charades. You could find more details from the Model 2 sections in the codebase. Beside of everything mentioned above, in order to make the codebase easier to use, PySlowFast will also release a tool for visualization, and more specifically for visualizing classification and detection results. Beside of that, a camera demo will also be released soon in order to help the quantitative evaluation on models. In order to share you directly how are we going to visualize the video detection results, we have already put a demo GIF in the folder of PySlowFast/demo. Feel free to grab the codebase and take a closer look at the demo GIF to collect more information. Besides of the demo GIF we put in the PySlowFast codebase, we also want to share you more visualization results on video detection in this tutorial. Note that the model we're using for visualization is PySlowFast model, and the model is trained on AVA 2.1 training set, and also the testing is performed on validation dataset. Here is a demo example on visualizing the video detection results on AVA dataset. You will be able to see there are green bounding boxes and red bounding boxes in the demo. The red bounding boxes are indicating the ground truth, and in the meanwhile, the green bounding boxes are the predictions from the human detector. Besides of that, you will also see some class labels and their corresponding confidence on top of each of the bounding boxes, which is clearly the prediction results from the model. On the other hand, you will also see the ground truth classes on the bottom of the bounding boxes. It is very interesting to see that even though a lot of actions are pretty hard and actually fine-grained, the demo is still able to correctly predict the label, and the prediction and the ground truth are majorly aligned. For example here, the model is not only able to tell the actions from these two persons, but maybe more importantly, the model is able to tell the fine-grained interactions between this gentleman and the lady. More specifically, understanding who is the one talking and who is the one listening. You will find more interesting visualization results from the video, and the slide will be uploaded, and feel free to download it to get a closer look at the results. The final demo tool from PySlowFast will be released later this year. We will continue play the video until finished. So after discussing the section of easy to use, we want to move to the next section, which is the modeling. The modeling includes two parts. We're not only supporting advanced backbone models, but also support state-of-art schedulers. So let's talk about the state-of-art backbone model first. So in PySlowFast, we are supporting many different types of backbones. It starts from the convolutional 2D networks to the infinite 3D networks, and then to the non-local block, which proposed from the paper non-local neural networks. Besides of that, we also provided some higher capacity model like slow and PySlowFast, introduced from the paper of PySlowFast networks for video recognition. If you are interested in what do we have for CPR 2020, PySlowFast is also releasing X3D networks, and our paper which will be presented on Tuesday. The author is Christoph, and the title is X3D, Expanding Architecture for Efficient Video Recognition. Besides of that, we're also planning to release the audio-visual PySlowFast for better support on multimodality research. The work is introduced by Fan Yi, Yong, Kristin, Jitendra, and Christoph. You can find the paper on arXiv now. Besides the state-of-the-art backbone we support in the PySlowFast codebase, we also support some advanced scheduler. Multigrid is another CPR paper from the team, which will be presented on Tuesday. The authors are Chaoyuan, Ross, Kaimin, Christoph, and Philip. The paper introduced a multi-grid method to significantly speed up the video training time by 3 to 6 times, while in the meanwhile achieving similar or higher performance. You can find the detailed implementation from the PySlowFast codebase now. By open sourcing the multi-grid method as one of the major advanced scheduler in the PySlowFast codebase, we hope it can benefit the video community, especially for the people who does not have enough GPU resource for computing. So after the modeling, we will talk about what kind of tasks will be supported by PySlowFast codebase. We will firstly talk about what are the supported datasets in PySlowFast, and following with what are the supported tasks by PySlowFast codebase. Currently, the PySlowFast are supporting many different datasets. Datasets like Kinetics 400, Kinetics 600, and Kinetics 700 for video classification. PySlowFast is also supporting AVA for video detection. Besides that, we are also supporting UCF and HMDB for small-scale action classification. And we're also supporting charade and something dataset as well. We are planning to support more datasets, and if you have your own datasets want to be supported by PySlowFast, welcome to contribute to the codebase. We are also supporting many different tasks in the codebase. Here are the tasks we support in the PySlowFast codebase. We'll discuss them one by one. For example, the default task in the codebase is video classification, which means if you grab the codebase and do not modify anything about the config or the running command, then you will train a neural network on the genetic dataset for the classification task. We also support video detection, which we mainly use the AVA dataset with additional bounding box and RY layers. By open sourcing audio-visual SlowFast, we are supporting multimodality video understanding in PySlowFast, which we hope the richer information from more modalities could help you for your own research. And because PySlowFast is very easy to hack, you can easily implement your own tasks. We will share you an example of how can you modify PySlowFast for self-supervised learning tasks in only 5 minutes. Before we walk through the parts that need to be modified in order to play with the self-supervised learning, I want to give you a brief overview of the main logic of the codebase. The logic of PySlowFast starts with parsing the config and build your models. Then you will have a backbone, as what we can see from the left side, built by the model builder. And then the next thing is to prepare the input. The video data loading is generally one of the most complicated and sometimes even confusing part in many different video-related code bases. The good news is, in the PySlowFast codebase, we have already carefully taken care of that, so you don't really have to do much. Start from loading the raw video from the local disk. Then the video will be decoded with a selective decoding for better efficiency. After that, a spatial and temporal sampling will be performed on top of the decoded frames to finalize the data preparation. After you collect the data, the model will be trained with the data we prepared, and batch norm statistic will be properly adjusted. After training is done, an evaluation will be performed after certain epochs. And finally, we will have performed a multi-view testing to get the final results. Then we want to simply share you how can we modify the PySlowFast to make it support a rotation-based sign for self-supervised learning. There are only 3 things you need to do. The first thing is simply adding an additional transformation to rotate the video frames, as what we can see from the right side in the code. Secondly, we need to implement the head for regression to the degree of rotation, which a simple linear with proper activation will be enough. And the last thing we have to do is write to a corresponding loss layer for the rotation baseline. So finally, we have introduced PySlowFast codebase with 3 directions: easy to use, advanced modeling, and supporting many tasks. I want to here thank the team for their great contribution to the PySlowFast codebase. The members from the PySlowFast team are Haoqi, Yanghao, Bo, Wenyan, and Christoph. Thanks for your great effort, and thanks for your great contribution to the codebase. If you are interested in or has already working on video understanding, no matter the task is video classification, detection, or self-supervised learning, or some multimodality understanding, we highly encourage you to try out our codebase. The link are here, and just feel free to grab it from the GitHub. We wish you could enjoy using the codebase and welcome everyone to contribute to the PySlowFast codebase. In the end of the presentation, I'd like also share you what's the new video research from the FAIR Innovation team on CVPR 2020. Here is multi-grade, a CVPR 2020 oral paper, which will be presented on Tuesday. The authors are Chaoyuan, Ross, Kaiming, Christoph, and Philip. The multi-grade method has been supported in PySlowFast open source codebase. X3D is another CVPR 2020 oral paper, which will also be presented tomorrow. The author is Christoph, and in PySlowFast, we are also supporting X3D as the strong backbone. Thank you for attending the virtual tutorial.